Hello friends, today I will discuss the distribution factor of alternator. In this video, the following points will be covered: necessity of this, definition of the distribution factor, terms used, and these terms used are explained with the help of the winding diagram, stator diagram, vector diagram, and from the vector diagram, single coil voltage in terms of slot angle will be expressed, and from using the same analysis the vector sum of all coils, that is m coils, will be discussed, and the same thing is also extended to calculate the vector sum of all the coils. And next, the distribution factor expression will be covered, and that will be calculated in terms of the beta, and based on this expression a numerical problem will be discussed, and that includes the harmonics if they are present. Let me consider first the necessity of this. This distribution factor in the alternator is necessary while calculating the generated EMF per phase in the alternator. Next, the definition of the distribution factor is like this. This distribution factor is represented by capital K suffix D, and that is equal to the resultant EMF of M coils divided by arithmetic sum of EMFs of M coils. This can be simply expressed as vector sum of EMFs of M coils divided by arithmetic sum of EMFs of M coils. Next, terms used here are conductor, that is also called coil side, and turn is nothing but two conductors. Coil means, so it may have any number of turns. For the time being, coil means only one turn, that is two conductors, that is nothing but two coil sides, and slots, so which are used in case of the stator. And full pitched coil means if the angle between the two coil sides of the coil is 180 degrees, such coil is called the full pitched coil. The number of slots per pole per phase is represented by M, and similarly the phase angle between the adjacent slots is represented by beta, and this will be discussed with the help of the winding diagram, stator diagram, vector diagram as follows. This is the winding diagram. So here there are three slots. This is one slot, second, third slot, and here there are two coils. This is coil 1, this is coil 2. Coil 1 have the two conductors. Similarly, coil 2 is also having two conductors. Coil 1, one conductor is placed in the first slot of the stator, while the second conductor of the coil 1 is placed in the second slot of the stator like this. That is, one is here, the other is here. The angle between these two coil sides, that is between these two conductors, are represented by an angle called 180 degrees. So when the angle is 180 degrees, then this winding is called the full pitched winding. The same can be analyzed to the second coil also. This is the second coil. Second coil, first conductor is connected to the slot 2, whereas the second conductor of coil 2 is connected to the slot 3, and the angle between this conductor and this conductor is 180 degrees. So this is also called full pitched coil. So the angle between the first conductor of the first coil, that is coil 1, and the first conductor of coil 2 is represented by beta. It is nothing but the slot angle, the angle between the two slots. This is slot 1, this is slot 2. That is represented by beta. The angle between these two slots is represented by beta. So to calculate this, so let me consider a numerical like this. So let us say we have a 3-phase 4-pole alternator with 48 slots. Then what is this beta and what is the number of slots per pole per phase also we calculate like this. Number of slots is equal to 48 and number of poles given is 4. The number of phases are nothing but 3. And first you can calculate number of slots per pole, that is 48 by 4, that is we get 12 slots per pole. Next, M is nothing but slots per pole per phase. So number of slots already known, that is 48, and divided by the number of poles means 4 into number of phases means 3. So then we get 4. So M becomes number of slots per pole per phase is equal to 4. And next, coming to the beta, that is slot angle. This slot angle is represented or defined like this: 180 degrees, this is for the full pitched winding, 180 degrees divided by slots per pole. Slots per pole already calculated as 12. So then 180 divided by 12 will give 15 degrees. So that is, in this analysis we found for this data the number of slots per pole per phase, M is equal to 4, and the slot angle is 15 degrees. Suppose we have the nth harmonic, n number of harmonics in the alternator. In that case, the definition of the distribution factor will be defined like this: sine of mn beta by 2 divided by m into sine n beta by 2. So if for fundamental, the distribution factor will become n is equal to 1, that is kd is equal to sine m beta by 2 divided by m into sine beta by 2. And this will be discussed at the end in the form of the numerical problem in more detail. So let me consider to explain the terms that are covered so far with the help of the stator diagram. This is the stator diagram housing the three phases, three-phase winding, and this is the OR phase, coil 1, and this is coil 2. So look at this. The angle between this coil 1 and coil 2 is nothing but 180 degrees. And the angle between the coil 1 and the next phase coil 1 or conduct coil side 1 is nothing but beta. So if you take the one stator and the one phase winding, then you can observe here this conductor is placed in this slot, whereas this conductor is placed in the 7th slot. The distance, the angle between this and this is nothing but 180 degrees. So it is called the full pitched winding placed in the stator of the alternator. And the same thing we extend for the whole coils of the alternator. So if there are m number of coils in the alternator, in each coil there are voltages induced, but in each slot there is a induced voltage corresponding to that coil. So in the next slot also there is a induced voltage in the coil, similarly next, but these voltages induced in the coils with respect to the next slot have the phase difference of beta like this. Similarly, like this. So individual induced EMF in each coil is same, that is small e, but whereas as a whole uh, M coils, then the voltage induced should be taken as vector sum. For getting that, so first one coil will be taken and that analysis will be extended to the number of M coils. So here AB is one slot coil. The induced voltage is we call as AB and that magnitude is E, small e. And similarly the next coil voltage that is in the next slot is BC, but its magnitude is small e, but it has the phase difference with respect to the AB by an angle called beta. Similarly, CD coil will have the phase difference with the previous coil voltage by beta, but the individual voltage is small e only. So this can be extended up to the whole system per phase, that is m number of coils per pole per phase. So this is shown up to by dotted lines like this. Now to analyze it properly, or to calculate the vector sum of m coils or vector sum voltages induced in the m coils, so first one coil will be taken here. This is AB coil voltage. This induced voltage across this is small e, and for this vector draw the perpendicular bisector and extend it backward like this. Similarly, each coil voltage draw the perpendicular bisector, extend the line backwards. Similarly for each coil, then all these bisectors will meet at a point called O, and then join the ends of this coil voltages also to the point O like this. A is also connected to O, B also connected to O, and C also connected to O, and D also connected to O, and the end conductor coil, end coil end point is also connected to O. And now look at the point here F. For AB coil voltage, the bisector point is nothing but F, and this forms the extend this line like this, and the angle between AB is nothing but beta, that is slot angle, and whereas AOF will make an angle called beta by 2, and from this take the triangle AFO, that is from triangle OAB angle is beta, and for AOF the angle is beta by 2. And now from triangle AFO, sin beta by 2 will become AF divided by OA, opposite side by hypotenuse. Opposite side is nothing but AF and hypotenuse is OA. So AF is nothing but E by 2, because AB value is small e. So AF is AB by 2. So we get here E by 2. So from this, E can be calculated in terms of beta and the OA like this. 2 into OA sin beta by 2. And if you look at this here, OA is equal to OB is equal to OC is equal to OD is equal to OP like that. And this we can calculate, use this for calculating the arithmetic sum of voltages in the m number of coils. This is the induced voltage in the first coil in terms of beta. That same thing can be used for calculating the arithmetic sum of voltages in the m coils, that is number of coils are nothing but M into individual voltage in the coil is nothing but E. So M into E. So then we can say M into 2 into OA into sine beta by 2. Since M coils are considered per pole per phase, the resultant EMF will make an angle of beta at the point O. Look at this. Earlier, one coil making an angle of beta at this point, and now M number of coils will make an angle of M beta like this. So for the single coil, we have calculated what is called sine beta by 2 is equal to the bisector value of voltage, that is AF divided by OA is written, that is E by 2 divided by OA. But whereas for M coils, we assume that the resultant voltage is ER, and its bisector, that is OJ, will make an angle called M beta by 2, because the whole angle is M beta, like beta earlier for single coil. So whereas for M coils, the angle will become M beta, and its bisector will make an angle of M beta by 2 with OA like this. And here is the triangle OA or AOJ. AOJ angle is nothing but M beta by 2. So for this, apply the trigonometry, that is sine M beta by 2. Sine M beta by 2 means opposite side divided by hypotenuse. What is opposite side for this? AJ divided by OA. What is AJ? AJ is nothing but half the AP. What is AP? Is nothing but ER. So AJ means ER by 2. So that we can see here, and we have seen for the single coil, that is from triangle AFO, sine beta by 2 is nothing but E2 by 2 divided by OA. And similar to that, we extend this to the whole coils. So that is, we take the triangle AOJ. So from triangle AJO, so sine M beta by 2 is equal to AP by 2 divided by OA. What is AP by 2? It is nothing but AJ. What is AJ is nothing but ER by 2. So denominator is as it is OA, and then resultant voltage from this we can write as for M coils is equal to 2 into OA sine M beta by 2. This is nothing but vector sum of M coil voltages, and say this is equation 1. And since OA is equal to OB, we can also replace that OA with OB like this. Then the resultant EMF ER for M coils will become 2 into OB sine M beta by 2. Similarly, the arithmetic sum of EMFs in M coils, which is already covered, can be written again like this: M into 2 into OA sine beta by 2. So that is nothing but since OA is equal to OB, we write M is equal to then is equal to M into 2 OA 2 OB into sine beta by 2. Say this is equation 2. And we know the distribution factor is nothing but KD is equal to vector sum of the voltages divided by arithmetic sum of the voltages. So in the equation 1, vector sum of all M coils is calculated, and in the equation 2, the arithmetic sum of M coils is calculated. So substituting them here, after defining again the distribution factor, we get like this: distribution factor KD is equal to resultant EMF of M coils divided by arithmetic sum of EMFs of M coils, that is equal to 2 into OB into sine M beta by 2 divided by 2M OB sine M beta by 2. After simplification, that is 2OB going to get cancelled in the numerator and denominator, then we get the sine M beta by 2 divided by M into sine beta by 2. And this is valid when the alternator do not have any harmonics in the waveform. So let us take a numerical for explaining better this distribution factor. Let us say we have a alternator, 3-phase alternator with 4 poles and 48 slots. and find the distribution factor. And the number of slots are given 48, number of poles are given 4, and number of phases are given 3. And we know the distribution factor, that is sine mn beta by 2 divided by m into sine n beta by 2, where n is the harmonic number. And first let us calculate what is m, that is slots per pole per phase, is nothing but 48 divided by 4, number of poles are 4 and number of phases are 3, then we get 4. And then beta is nothing but slot angle, that is nothing but 180 degrees divided by number of slots per pole. So we know number of slots per pole is nothing but 48 by 4, and 180 divided by this 180 by 48 by 4 will give 15 degrees. So for calculating the distribution factor, we need m and beta, so we obtained m and beta, so we can apply it here, assuming that the alternator do not have any harmonics, that is only fundamental is present. Then in that case n we say is equal to 1. Then the formula will become like this: sin m beta by 2 divided by m into sin beta by 2. Substitute all the values here which are calculated for the given problem. Then that is m is equal to 4, beta is equal to 15 degrees. Then kd will become sine 4 into 15 degrees by 2 divided by 4 into sine 15 by 2. So then after simplification we get 0.9575 as the distribution factor. Suppose the alternator has the second harmonic in the waveform. In that case, that n will be taken into account for calculating the distribution factor, that is sine second harmonics, means in place of n we substitute here 2, and rest are same, that is beta sine m beta by 2 means m is nothing but 4 and beta is 15 degrees by 2, and divided by 4 into, that is m means 4, and then sine second harmonic 2 into beta by 2, that is 15 by 2. After simplification we get 0.835. If the second harmonics are in general, when the harmonics are present other than the fundamental, the distribution factor reduces. Once the distribution factor reduces, automatically the voltage generated from the generator also reduces.